Okay, hi, welcome everybody. Welcome to Math Teachers Code. I'm Yoni Nazarathi. This is our sixth and final session of Math Teachers Code. We've had a six-part series, and thank you for those of you that are joining live. Hello also to those of you that are watching the recording. So what we're going to do today is we're going to recap pretty much everything that we did in the last 5 sessions. And also do a bit of optimization. The format is slightly different than the previous sessions. In the previous sessions I coded live and we did it step by step. Now we're going to do something slightly different. We're going to head on to the comments section of this video, and what you'll see is related links. You'll see a formatted Jupyter notebook for this session. And we're going to download this notebook and upload it to JuliaBox. So if you haven't done this before, you might as well do it now. You simply go into JuliaBox and log into JuliaBox. The way we're doing this is via email in our case. For me in this session, it's mathteacherscode@gmail.com, but you'll of course use your own authentication. And I'm logging into JuliaBox. And at this point, I can launch my JuliaBox instance. And while this is happening, I'll go over to this other tab and download to my local computer the IPYNB. That's the Jupyter notebook file. You can also see the notebook file on PDF, but you'll download, in this case, the IPYNB, download it locally. So it's downloaded to my downloads folder. And now here back in JuliaBox, I'm already inside Math Teachers Code. In my case, there are the previous 5 sessions which we had. You can also get them from the comments box. But I'm going to now hit the upload button and upload the IPYNB that I just downloaded, and that is Math Teachers Code Summary 2018 IPYNB, and I'll open that. And what this does is, and I'll hit upload for it here, and this has uploaded the IPYNB file into my JuliaBox instance. Okay. So this is how you transfer files from your local computer, which can come from anywhere else. In our case, it came from this place, from the comment section of the YouTube video. This is how you put them in your JuliaBox instance. And now I'm going to hit this link, and I'm in the notebook Math Teachers Code 2018 Summary, and we are almost ready to go. Now, this summary is actually interesting, is an interesting thing for you to see as teachers, not just because of the fact that it summarizes everything that we've done, and we'll go over this stuff, but also perhaps to see how I formatted it. So if I click this first cell, for example, what you see here is the markdown code that creates this first cell. You see this cell is a markdown cell, it's not a code cell. And you can use a few basic markdown formatting commands to add graphics, links, images, headings, etc., etc. So if I hit Shift Enter again, the cell will reappear again as formatted markdown. But you see I put a link to this URL, which happens to be the 1 on Epsilon logo, and I put some other links and text there as well. So wrapping up Math Teachers Code 2018, this notebook contains most of the key elements from what we've done in sessions 1 through 5. This is session 1 to 6. You can of course head on to the YouTube channel and subscribe to us in the YouTube channel if you like this. You can also use Epsilon Stream to search for Math Teachers Code. And if you like what we do, please register with us just to show your appreciation. You can also follow us on Twitter @1onEpsilon. So what we have here is quite a big notebook and quite a big work order for today. We're going to follow everything we did from session 1 down to session 2, continuing in session 2, moving on to session 3, more in session 3, session 4, session 5, until we get to session number 6, which is happening right now. So what I will do actually is start with session number 6, which is just a finish up on stuff we didn't manage to do in session number 5, and that's going to be some very basic optimization. So we're going to speak about extremely basic optimization, but optimization that you code yourself and you can code live in front of your mathematics students. And then we'll go back and see the other sessions. So notice that in each of these sessions, I've added links to this notebook, both to the YouTube videos and also to related things such as the Global Math Project, and also to Epsilon Stream, to certain spots in Epsilon Stream. For example, here we have computing pi via a series approximation, and you can hit this link and open series in Epsilon Stream. So in Epsilon Stream, you can pretty much search for anything in the world of primary, secondary, and exploratory mathematics, and you'll get some of the best content that our team has curated for you. All free, without adverts. Okay, let's get to session number 6 and do a bit of optimization and then move on to the review. So in the previous session, I've just zoomed in a bit. So in the previous session, we actually spoke about the quadratic equation, well, the parabola. You spend a lot of time in algebra teaching this, trying all kinds of variants, learning how to complete the square, learning how to use the quadratic formula, finding minima or maxima, finding roots if they exist, etc., etc. And one of the things is clearly optimization. Now, from a brute force calculus perspective, the way you would find a critical point in the parabola is clearly take the derivative. And notice that this cell here is a LaTeX cell, right? So if I click on it, you see the markdown, and this is LaTeX code. You don't have to know this LaTeX in order to use math teachers' code or in order to use Julia box, but it helps just to kind of present things. So the derivative of this second order polynomial is clearly 2ax plus b. And then if you equate 2ax plus b to 0 and solve for x, you get that x is negative b over 2a. And often students memorize this. Sometimes they understand how it works. Sometimes, unfortunately, they don't. But of course, we help them do that. That x is the local minimum or local maximum of the parabola. So in this case, what this code does here is we simply have the three constants a, b, c. This is the same parabola we had in the previous session of Math Teacher's Code. And then we define this function f1 of x as ax squared plus bx plus c. So this function actually uses the variables outside of its name scope, a, b, and c, and they are defined here globally. And then we set a grid, an x domain between -3 and 5 in this case, and plot the x domain against the function applied to x domain. So this little dot that we see here is quite a powerful operation. It's a broadcast operation. It applies the function f1 to every point in the x domain. Now the analytic argmin, the x that minimizes, in this case, well, we know it minimizes because a is positive, the parabola is upward facing. We could have obviously taken a second derivative, but the analytic argmin is negative b over 2a. Okay. Notice, by the way, in Julia that you could put a literal 2 next to a variable a, and that just means 2 times a. Okay. And then we're going to plot this analytical argmin with the function applied to the analytical argmin, make it green and put a point size in 20, and we see the minimum. So good. This was nothing but using Julia as a graphics calculator. But now let's try and find this minimum without calculus. Sure, calculus is nice and great, but we can't always use it. Let's just use a brute force approach. Now, of course, minimization of functions, this is a whole field, and minimization, maximization, optimization. There are many, many complicated algorithms. Also, a lot of modern machine learning is based on minimization, maximization. But here we're going to do pretty much the simplest thing possible, and we are going to search for the minimum. So how does one search for the minimum? Let's look at this graph and think how we would search for the minimum value. Well, what we can do is we can iterate from -3 to 5. We're going to search within a certain range. We're going to iterate from -3 to 5. And every time we're going to see if the value of the function in that point is smaller than all the other values that we have seen before. And if that's the case, then we're going to remember this new value that we've met as the current minimum. And we'll continue this iteration until we finish the range, at which point we know what the minimum is. So here is the code for that. So again, in this session, we're not going to do the live coding, but rather I've pre-prepared this code simply so we can cover quite a bit of content in the session. We'll get back to the review in a sec. And what you have here in line 1 is the variable argmin, and in line 2, the variable minval. Okay, so I'm initializing argmin as nan. Now nan stands for not a number. This is actually a numerical value, which says, well, this is actually an undefined value. Argmin is an undefined value. As opposed to that, minval is also not really a number, but we're setting that to inf in the sense that minval is infinity. Why is that? Well, infinity is greater than any other value. That is not infinity. It's greater than any other finite value computationally, and that's going to be useful in the iteration, as you'll see in a sec. So now we have the loop. This is a one loop piece of code between lines 4 and 9, and what we're doing here is we're iterating over every x in x domain. X domain, remember x domain was this range from -3 to 5, in this case in steps of 0.01. So we're looking for x in x domain, and we're iterating. X is going to be the first value in x domain, the second value in x domain, etc. And each time we're going to check the logical condition in line 5, and that is if the function f1 at x is less than the minimum value that we have found up to now, then we do lines 6 and 7. Now lines 6 and 7, we can basically call them we've found a new minimum, right? Now in the first time we iterate, we're certainly going to enter line 6 and 7. So for the first x, because minval is going to be infinity, and f1 of x is going to be less than infinity. Afterwards, well, sometimes we'll enter this line, sometimes not. In the case of this parabola, we'll continue entering this code until we reach here, until we reach the point 1, at which point we'll never enter these lines again. But that's a detail. Okay, so in line 7, we set the new minimizer to be x, and the new minimal value to be the function of x. Okay, that's already an important point. So if you show this code to students as you speak about minimization, there's no mathematical Newton-Leibniz hocus pocus here happening with derivatives, but it's just searching for the minimum. Still, this is algorithmic thinking about, hey, there is the argmin and there is a minimal value. These are two ways to describe the minimum, and argmin and minval describe the new minimum that has been found. So we're going to run like this for all x and x domain, at which point we'll say found a minimum at, and I haven't used this type of formatting yet, I don't think. So if you put inside a string in println, if you put inside a string $, and here you can put an argument, this argument is actually a program variable. In this case, it's argmin. So it writes, we have found a minimum at 1. Indeed, this parabola is minimized at the point x equals 1, with a value of $minval, and that is minval, which is f of 1. And that's it. That's it. Now, this is such a common type of programming construct, this searching for minimum using brute force search, that there's actually a built-in command for that, and that's called findmin. Findmin. Now, the way findmin works, you can look later at the docs of findmin, or even I'll do it now for a sec. Just question mark findmin, just so you see it. So the way findmin works, you give findmin a vector, or an array, a list of values. That's what you give to findmin. And findmin is going to search for the minimal value, just like we did here in this list of values, and it's going to return a tuple. So you see, we're getting here as a return argument from findMin, not just the minimal value, but also the minimal index. So when a function returns a tuple, returns, well, 2 or more elements, in this case it's a 2 tuple, we can take the return value and put the first one in min_val and the second one in min_index. The help is not coming up for findMin here, but it might in a sec. Okay, so min_val is exactly going to be this thing, which is -9. That's min_val. As opposed to that, min_index is going to be the index of the array that we've given findMin. Now we've given here findMin the array f1 applied to x domain. Okay, that's what we've given to findMin. So it's going to return the index. So let's see what we print out. Found a minimum at index, $min_index. Now in this case, min_index is the number 401, which happens to be the index in the array of values, which is of minimal magnitude, 401. 401 doesn't have any meaning on this x-axis between -3 and 5, but it is the index within this range, -3 to 5, which happens to have the minimum. So look at how I write this. Found a minimum at index 401, which is at x equals 1. How do we know x equals 1? We'll take this range x domain and get the min_index element of that. So that min_index happens to be 1 and has a value of -9. So this cell does the same as the previous cell. I'm actually not sure why this question mark findMin is not working. I'm going to restart the kernel. So you see, you can go to the kernel menu and hit restart. That restarts the kernel. Let me actually run this cell again. And I'm not sure what's happening here, but it's actually not it's not a problem for us per se. Okay, well now kernel started and this worked. So here we get the help for findMin. So findMin describes how findMin works. Okay, so that was minimization. Clearly there's also a findMax, which does maximization. It's kind of the dual function of findMin. And that is all I'm going to say about optimization. Indeed, this is very basic optimization. I hope you agree with me that actually coding this simple line of code, the simple few lines of code, live or perhaps not live in front of your students, and actually showing them how minimization would be done on any arbitrary function can be useful. Okay. I think it actually brings out appreciation for the beauty of calculus and also other methods of minimization and maximization that are much more complicated. Okay, we're now going to scroll up in the notebook, and we're going to go all the way back to the start of our math teacher's code, and we'll review everything that we've done. I probably won't have time to discuss every single line of code. I'll just highlight a few bits from here and there. You can go to the specific YouTube videos where we've actually coded this live, and you can try and code this live yourself, and you can try and make it work. You can of course modify it. Let us know in the comments what you do. Let us know what worked in front of your students, what didn't, etc., etc. So we'll start in session number 1, where we actually spent quite a bit of time introducing JuliaBox. Again, you can go to JuliaBox, you can go to Julia Computing. So I'll search for Julia Computing, and that is the company that gives us JuliaBox. It gives us as a free service. There are also, of course, some paid services which give higher performance, etc. So that's JuliaBox. You see that they have a variety of other products. That's Julia Computing, and this is of course all part of the Julia language. Well, it's not all part. The Julia Computing is a company where the Julia language is an open source endeavor taken up by hundreds and thousands of researchers around the world, and that's what has made Julia. Okay, so in the first session we spent quite a lot of time speaking about Julia box, but then we actually got going with this example, which was the hailstone sequence and the Collatz conjecture. So the hailstone sequence, we can understand it here from line number 2. It is a sequence of numbers where the next number is going to be either the previous number divided by 2 or the previous number multiplied by 3 add 1. And that depends on if the previous number was even. So here in line number 1 we define a function which checks if x is even. And number is even if its modulo divided by 2 is 0. If the remainder of division by 2 is 0. And then in line number 2 we define the next function. We say if the function is even, then if the number is even, take the number and half it. This halving in Julia promotes it from a floating point type into an integer type into a floating point type, and then we'll convert it back into an integer. Otherwise, otherwise, multiply by 3, add 1. And then this first function we had here, print Hale, what it does is you give it an initial number x, and it loops, well, effectively forever, although the Collatz conjecture is that this loop actually halts at some point. Because the halting condition is that x is 1, right? So you loop as long as x is not equal to 1, and you halt when x equals to 1, and then you print x, not print len, but just print with a little space after the x, and make x be the next x. Okay. That's a function print Hale. There is a similar function which is called Hale Array, in which case we get an x and we create an array which will at first just have x in it, and then we loop again until we hit 1. The conjecture is that we'll always hit 1 at some point, and we put x to be the next of x, and we push into the array, x, so that appends the value x into the array, and we turn the array. So then to plot this thing using pyplot, and let's say we start with a value of x27, so that's start 27, we're going to give that start into Hale Array. So start is the name of the global variable here. We're giving it into the function Hale Array here, and then Hale Array treats start as x, or x is a value of 27. And works on that. And out is going to be an array. N is going to be the length of the array, in which case it's quite a long array. And we're going to plot the integers, the indices 1 to n versus the array. And here you see the plot of the hailstone sequence. You see how crazy it is. Starting at 27, going to 82, continuing to 41, until it finally plummets down and hits 1. Okay, 27 is a quite special number in this case. Okay, so that was the hailstone sequence, the Collatz conjecture. You can search for that in Epsilon Stream as well. We also have a blog post dealing with it. And there's actually quite a lot of activities all around the web dealing with this sequence. Okay. In session number 2, one of the first things we did was a linear congruential generator. So we actually spent time creating this function which we called myrand, which was our own random number generator. And we use constants a, c, and m to be this wacky number. C is 1 and m2 to the power 32. We started x as a seed, and we set an array to be all zeros of type float 64. Okay, and then we loop over the array, and again we do a recursion. Yeah, so this recursion here, this is equivalent to the next function which we've used here. This type of construct, right? It's a recursion where the next value of x, in this case, it's a linear congruential recurrence, so it's a times x plus c, that's the linear, or well, the affine part, but the linear part, modulo m. Okay, and this is how the most basic pseudo-random number generators work. And this constant, together with this constant, is one of a few known constants that give a pretty good sequence. And then we pushed into the array not the actual value, which lives between 0 and 2 to the power 32 minus 1, but rather the value divided by 2 to the power 32. So hence, what we're sticking in array in line 9 here is a number between 0 and 1. And we turn the array. So just to see this in action, this function which we've just defined, we've given it some arbitrary seed, 2001. We said let's give a million numbers, and that's the data. And here we're actually, well, this code doesn't do anything because we're not printing it, but this is an arithmetic mean, this is a variance, and this is a minimum and the maximum. And here when we take 200 bins, and this is how we plot a histogram using the PyPlot package in Julia. There are other plotting means as well. We get the histogram of the values. Okay, this histogram in no way tells us that this random number generator is necessarily good. It simply says that it appears to have what is a uniform distribution. It doesn't say anything about the correlation between values. Okay, so that's a linear congruential generator. Then we moved on to the central limit theorem, which in many ways is much more exciting, and we've actually seen the central limit theorem using our own random number generator. So what we do here in line number 3 is, in line number 1 is create 4 seeds. These are 4 arbitrary numbers. We're going to take 10 to the 6 values. I'm going to plot the histogram with 200 bins. And here we create 4 arrays, each one with 1,000,000 values. Data 1 up to data 4. So these 4 arrays use this function here, myrand. Okay, we could have used the built-in rand as well. What we do now is we sum up data 1 plus data 2 plus data 3 plus data 4. This is an element-wise sum in Julia. So we're summing up the elements of the vector data 1 with elements of the vector data 2 with elements of the vector data 3 with elements of the vector data 4. Okay, I'm just running this. So I need to run the previous cell to define my rand, and then I can run this cell. And we're plotting the histogram of that. And we're also adding to the plot, this is the density of the standard normal distribution. And here we take the standard normal distribution and we subtract from it mu and sigma. Okay. And mu and sigma, oh, I see. Mu and sigma were defined. I'm not sure actually where we define mu and sigma. Oh, I see. Mu and sigma are arguments to the function g, and then the mu is going to be 2, and the sigma is going to be square root of 4 over 12. Okay, and we know this because of the mean and the variance of a uniform random variable. But the point is that these lines here, lines 13 through 18, plot this standard, well, not the standard, plot this normal density with a mean of 2 and a standard deviation of square root of 4 over 12, and we're plotting that against the histogram. This thing becomes slightly interesting if you don't plot data 1 and data 2, and this is how I often teach it to students. Don't do the sum of data 1, data 2, data 3, data 4, but just, for example, the sum of data 1, data 2, in which case, you see, when you're summing up 2 uniforms, you get this triangular distribution. We could have adjusted mu and sigma here, these 2 values, to move this orange plot over them. But then when you add more uniforms, you're quickly converging to something which appears to be a normal distribution. The sum of 4 uniforms is certainly not normal. The maximal value is going to be 4 and the minimal value 0, but it's certainly very close, and that is a central limit theorem. And that's what makes the normal distribution so ubiquitous in nature. Okay, so that's what we had in session number 2. In session number 3, we moved on to computing pi via a series approximation. Okay, and a few other ways of computing pi. Now this is in no way the best way to compute pi, but it's actually just quite neat. So this series here, the sum of 1 over k squared, k going from 1 to infinity, miraculously happens to be pi squared over 6. So if we were not to sum it up to infinity, but only say up to some finite big number, in this case 10,000, and then multiply by value by 6 and take the square root, that should give us a pretty good approximation of pi perhaps. And this is what we do in this line. We're simply summing up 1 over k squared, or k going from 1 to n. Okay, this thing here that I've highlighted, that's called a comprehension or comprehension array. It evaluates the value 1 over k squared with k running in this range. It's a very powerful programming construct that you can use in Julia. It also exists in Python and a few other languages. It doesn't exist in the old languages, JavaScript, C, etc. And then we're summing up over this array. We're multiplying by 6, and we're taking the square root, and that gives us this approximation of pi. That's an approximation. Okay, that is a dry way of approximating pi, but it's cool that because it uses a series. But here is a much more picturesque way, and what we've done here is we've inscribed regular polygons. Now, as a math teacher, you might have done this, perhaps with slightly more advanced students, in application of trigonometry, where if you actually compute pi, and you can actually get a formula for the for these lengths of the length of the base of the isosceles triangles, which make up the regular polygon, and then you sum it up. But here we've actually done this from first principles. So let's see how this works. So first of all, in line number 2, we just create a circle. Okay, create a circle. The angle runs, in our case, we want to think in degrees. Okay, so it runs from 0 to 360, in this case of steps of 1, and we're plotting the cosine of the deg to rad angle and the sine deg to rad angle. So circle points is an array of points, so when we plot this, it gives us the blue circle. This creates an aspect ratio of 1, and this plots a circle. But then we created our own function, make points, makes PTS n, which gets n, and n is the number of elements in the regular polygon. So if, for example, I put a make points with 3, we get a regular polygon with 3 points, a triangle. Make points with 4 gives us a square. Make points with 5 gives us a regular pentagon and a regular hexagon, in which case all of the 6 triangles inside this hexagon are equilateral triangles. So hexagons are kind of special and neat, etc., etc. So the angle here, theta, is an internal angle. Sorry, it's not the internal angle, it's the angle which between the angle of the arc between 2 adjacent points, and this is how we create these 6 points. So then this plots the points and just connects and creates a polygon. Now we've coded our own distance function. We can also use the norm function, which comes with the linear algebra package, but I haven't spoken about that. We've just created our own distance function. This uses exactly the distance formula. And then we just apply the distance formula to the adjacent points and get our approximation for pi. So pi happens to be 3 if your circles happen to be hexagons. It happens to be 3.129 approximately, 3.1286 if your regular polygons happens to be 20 gons. If your polygons are 100 gons, then pi is 3.14, yada yada yada. Okay, so this is an extremely visual way of seeing pi, And we actually haven't used analysis to compute this. Of course, one doesn't have to carry out this line 19, by brute force, right? You can actually use trigonometry and get a nice formula for pi, for this approximation of pi based on an n-gon. You can also put a polygon outside the circle, etc., etc. Okay. Having done this method, let's go to a kind of a much more brute force method. But I kind of like it because it's just so simple. So what we're doing, and it also introduces the notion of pixels to students, which is kind of a cool notion. I mean, a picture is nothing but a matrix with the elements of the matrix indicating the color or the hue or something like that. In this case, this is kind of a two-colored picture with the colors being either yellow or purple. Yellow is 1, purple is 0. So we're using pyplot, and we're creating this matrix of zeros, and then we're running over all the elements of this matrix. So this is, I think, the first time in math teacher's code where we've seen a for loop inside a for loop. That's called nested for loops in a sense. So I runs from 1 to n, and j runs from 1 to n as well. So this code, which I'm highlighting now, lines 7, 8, 9, happens n squared times. And each time we're actually checking if I squared plus j squared is less than or equal to n squared. That's, again, Pythagoras theorem. Then we're saying, well, that point in the matrix should be a 1. And that's how we create this matrix. Okay? So here's a 20 by 20 matrix. Here is a 100 by 100 matrix. Here is a 500 by 500 matrix. You don't want to go too crazy with this because you can run out of memory quick. Okay, 1000 by 1000 matrix already has 1,000,000 entries that we can still handle, but not a whole lot more. Okay, so the way we now approximate pi is we simply sum up the number of elements in this matrix, which is just summing up all the elements that are 1, divide that by the total number of elements, which is n squared, and then multiply by 4. And that's our approximation for pi. So a very kind of brute force simple approximation by counting pixels. If you're into this and you kind of like it, think how to use such an approximation for computing integrals. Right? So those of you that are actually teaching AP calculus students or similar types of students integrals, we teach them all these wonderful rules of calculus, which are brilliant. And sometimes we also do a bit of numerical methods, trapezoid methods, and other methods. But this is actually, in a sense, you can approximate integrals in this way too. If you create such an example, let us know. Okay, a different way of computing pi would be with random points. So now we'll take, this would be the lower right quadrant, which we did here for the this approximation. But for this approximation, in this case, let's talk about the top right quadrant. And let's just throw 10,000 random points. Okay, 10,000 random points. By the way, each time I'm hitting escape and L so that you see line numbers, so I can speak to you about line numbers if needed. So we create the points as by James Tanton. You can check out James Tanton's Twitter here, and there's always some interesting questions that he poses. And this was one which I particularly enjoyed. It says, n has one digit in base n plus 1. I agree. And more digits in base 2. Sure. Let an be the average number of digits of n when represented in bases 2, 3, 4, up to n plus 1. So we take a number n, and we represent it in all these different bases. And for each base, we count the number of digits. And then we look at the average, the arithmetic mean of that. So this is this function of a of n. This is James' question summarized in one function. It says, let's look at the mean of this comprehension. Okay, the mean of this thing. What is this thing? We'll let the base, run from 2 up to n plus 1. And we'll look at the length of the number of digits of the number n with base b, nothing more. If you plot this function a of n, this function is a function of n, you actually get this kind of cool pattern. And notice that it seems to be at first just below 2 and then it's above 2. And as you increase, let's plot the first 1,000 values, for example, it seems to be getting very close to 2. For example, A20,000 is 2. So I believe that this actually goes to 2, and it's actually not so hard to derive it. Try to do it yourself and let us know in the comments, or let us and James Tanton know how you went. Okay, moving on from this kind of classic base representation of numbers, let's move to the N1 machine and exploding dots. Now, exploding dots is actually a beautiful subject. So if you go to the Global Math Project, check out all the resources associated with Global Math Project, exploding dots, and such. You'll find a whole bunch of very cool resources dealing with this way of learning arithmetic, base representation of numbers, rational numbers, irrational numbers, and a whole bunch of things in algebra. And it all has to do with this construction, which is called, say, the N1 machine. There is some more general constructions, but let's speak about the N1 machine. The way the N1 machine works is you consider an array of boxes, where in each box, if there are n dots, they join up together and explode and move one to the right to become one dot. That's the N1 machine. And if you watch a few of the videos, for example, here's exploding dots on Epsilon stream, but you can get it elsewhere as well. So you watch a few of the descriptions of exploding dots, you'll see the power of this method, and you'll see how you can actually do arithmetic with it and really understand what number means, what numbers mean, I should say. So what we did here is we've actually implemented the N1 machine, and let's see how this works. So M here, 5, is some artificial upper bound on the number of slots. Let's take base to be 10. So this is the B1 machine, okay? But well, the B will be 10. What we do is we get a state of the machine. So for example, this is a machine, okay? So there are 19 dots here, and 0, 0, 0, 0. And then these 19 dots, oh, okay, what we're seeing here is for base equals 2. Okay, this is for base 2. This is for base 2. So then these 19 dots, 2 of them are going to explode, kabow, and you've got 17 dots and 1 here. And then there's 15 dots here, and 2 of them will explode, and you'll get 13 and 3. And these explosions continue until you're ending up with this situation, where you have 1, 9, 0, 0. But then these 9 dots, you've got some pairs of dots that want to explode. So you've got an explosion, and another explosion, and another explosion, and another explosion. And finally, you end up here when there are no explosions. And this, read left to right in this case, is a base 2 representation of the number 19. So if, for example, we were to revise this code and do it with base 10, you see, this is the base 10 representation of 19. Okay. So that's exploding dots, and you can explore this code more. I won't spend more time on that. Then we moved into session number 5, where we at first talked about the roots of a quadratic equation. This is where I started this session today, and then did a numerical search for roots of an equation. So what did we have here? So what we had is we started with this function, this parabola here. And these are hard-coded solutions to the parabola just using the quadratic formula. So the solutions to a parabola with coefficients a, b, and c are, as you know, that's a quadratic formula. This is the negative b minus square root, and this is a negative b plus square root of the discriminant. Right? That's a discriminant. Okay. And here all we do is we just create a plot of this. So the solutions are these two solutions. The x domain, we just choose some domain, which is sensible in this case, between -3 and 5. And we plot the x domain versus the function f1 applied with the broadcast operator to the x domain. And that's the red curve, that's a parabola. We also plot the x-axis, in this case between -3 and 5 with y-coordinates of 0, 0. And we then plot the solutions. So here is the first solution and here is the second solution, okay, as green points. Okay, and the roots of this equation are -2, 4. Fine. But let's search for that using brute force search. And for this we created our own function which we called find roots. Now this is a kind of a nifty function because what it gets as a first argument is a function in its own right. It gets the mathematical function f. Yeah, so we're going to apply the function find roots to the function f1, which happens to be our specific parabola. And the way find roots works is we actually create a sine array, which is the sine function of the function f applied to this grid. Okay. So the sine function is either -1, 0, or +1, and we're creating an array of roots. And then we run over this array. Well, that's in line number 8. That's an iteration between line number 8 and 12. And then each time we check if there was a sign change, and also the sign happened not to be 0, we explain in the video why we do that, then we have found a new root. So push into roots the new root that we found, and here we have a linear interpolation for the roots, makes it slightly closer to the real root. This is of course important if grid is not fine enough. Okay, and we return the roots. So for example, if we look for the roots of this parabola, here we get numerical solution of this roots. Now in no way is this the best way to do to find numerically the roots of a function. This is a very brute force approach. However, just coding this and doing it live in front of students, or doing a variant of this, perhaps illustrates what it means to numerically find roots. It also illustrates the beauty of actually the quadratic formula, because the quadratic formula is such a low complexity way of finding roots. So line 7 here does much better than this whole code. Now, of course, if you get to some crazy wacko functions, take, for example, f1 of x plus 2 cosine 20 of x, which is this parabola which is, I should say, contaminated with this cosine function of magnitude 2 and of quite high frequency. Finding the roots of this is a bit harder. I actually don't know if we can do it analytically. But here the find roots function looked at all the places where this cosine-ish parabola crossed the horizontal x-axis and said that these are the roots. Specifically, if we want to plot the positive roots, so let's take a finer domain between 3.5 and 4.5. You see, if we're looking here between 3.5 and 4.5, the function. Okay. Then we will filter just the positive roots and plot these positive roots, and we see that the green points are indeed the points, or appear to be in the place where the red function crosses the blue horizontal x-axis. Here, by the way, in line number 5, we've used the filter function, which takes an array and returns an array which is potentially smaller, with only the values for which this function is true. Now what I'm highlighting here is called an anonymous function, and this is a function that takes a value x and returns true if x is strictly positive. Okay, that's a filter. We've used filter before in this code, in these code examples, but not with an anonymous function. So that is it. And then we're here in session number 6, which we started today and finished today. And that's a lot. That's a whole lot of material. It's probably a whole lot of material for you to explore, especially if you haven't been coding before. If you have done some coding before, you can use this as just as an example on how to use Julia. I do think Julia is quite a nifty language to use for the purpose of mathematics education, because it's a relatively simple language. It's quite easy to read, and you can of course get it free with JuliaBox. So on this note, I'll stop here, and thanks those that have been following us in this series. Please try our Epsilon Stream app. It's really a useful resource that gives you almost anything you need in the world of primary, secondary, or exploratory mathematics. And if you like what you see, register with us and help us spread the word. Thank you. Yoni Nazarati here. Bye-bye.